Previously, we have been discussing about the geometric representation of signals, and towards the end of the last lecture, we were talking about the length of the signal in terms of the norm. How do we get the norm of the signal? And then we talked about the energy of the signal from its vector representation, and we got a relationship between the energy and the norm, that the energy is the square of the norm. And we also did how we can compute the dot product between two signals, and finally we stopped at computing the distance between two signals, right? So we found an expression to compute the distance between two signals when you have the signals represented in a vector form, in a geometric form, that is. So we got this expression for the distance between two signals, where these Sij and Skj are nothing but the vector elements of the signals Si and Sk. Now from that we deduced that the norm of the difference between the two signals is basically the distance between the two signals Si and Sk. And today we are going to show how we can compute the angle between the two signals. So if we have two signals like this, how do we compute the angle between them, and how we can do that based on the values of the vector elements of the signals. When we have the signal represented in a geometric form, how do we compute the angle between the two signals? Okay, and that is our topic for today's lecture. And towards the second part of today's lecture, of this lecture, I'm going to give you an introduction to a process of finding the basis functions, right? So to get these values Si1, Si2, we need the basis functions. If you recall, we need these values, these basis functions phi I and phi j, and phi 1 of t, phi 2 of t, and so on. So we'll do that towards the end of this lecture. Okay, so we'll start off now with the process of determining the angle between two signals, or the angle between the geometric representation of two signals. To do that, let us first of all draw the diagram for the two signals, just as we have here. Okay, I'm just going to redraw the diagram again, and then we will start analyzing, and we are going to use basic concepts of geometry to get the angle between the two signals. So we have this geometric representation of the two signals. The first signal is S1 and the second signal is S2, and we have the projections of those signals onto the basis function. So the basis function here is phi 1 of t, and the basis function here is phi 2 of t. Okay, again I'm showing this for a two-dimensional case, and that would apply for any dimensions. Okay, we can extend the ideas, the same procedures for any dimensions. So what we have here, the projection of the signal x1 on the basis function phi 1, so that is S11, and the projection of the signal S2 onto the basis function phi 1, so that is S21. Similarly, the projection of S1 on phi 2 is S12, and that projection of S2 on phi 2 is S22. So we have the projections of these signals onto their respective basis functions. And now we will define the angles. So let's say that the angle between S2 and the x-axis, okay, this angle, this total angle here, we'll call this as angle A. And the angle of S1 with the x-axis is angle B, and then we will call the angle between the two signals as theta. So we will denote this angle here as our angle theta, and then we are going to use some basic geometry to find this angle theta. So let's give some name to the vertices, because we are going to use some triangles. So this vertex here, we'll call it as A, this point we'll call it as B, and this point where we have S21, we'll call it as C. I'll write it here as C, and this point here I'll write it as D, and the point corresponding to S11, I'll call it as E. Okay, so we are interested in finding the angle theta, and if you notice from the diagram, the angle theta is nothing but the difference between the angle A and B. So A is the total angle from the x-axis to S2. B is this angle, so the difference between A and B, that's A minus B, is going to be theta, right? So the first observation we make here is that the angle theta between the two signals S1 and S2 is nothing but the difference between the angles A and B from this diagram, and we are going to use this in our analysis. Okay, so we have the first observation from this diagram is that theta is equal to the angle A minus angle B. So angle theta is angle A minus angle B. So we are going to use this fact in our computation. Now from we are going to use some triangles. Okay, we are going to use this triangle ABC. So that's ABC. From the triangle ABC, we can compute the angle A using cosine theta or cosine of A, and we know cosine of A is adjacent opposite by hypotenuse, right? So opposite is this, which is S22, by the hypotenuse is nothing but the length of S2. The length of S2 is nothing but the norm of S2, right? So now we are going to write that from triangle ABC, we can write cosine of angle A as cosine is opposite by hypotenuse, so the opposite of A is this line, and this line is having a height S22. By hypotenuse is this, because that's a right angle triangle. Hypotenuse is the length of S2, which is the norm of S2, right? Length means norm. So that's going to be S22 divided by the norm of S2, or that is the signal S2. So that's cosine A, and similarly we can write sine A as adjacent by hypotenuse, which is in the same triangle. Sine of this angle is adjacent, means this angle, that's S21 divided by the hypotenuse, which is the norm of S2. So sine of A is S21 divided by the norm of S2. Okay, so we have cosine A and sine A for from the triangle ABC. So that's our triangle ABC, that triangle here. Okay, now from that we have cosine A and sine A. Similarly, we can have cosine B and sine B from triangle ADE. So we'll use the triangle ADE. So from triangle ADE, we can write cosine B to be equal to opposite by hypotenuse. The opposite side is this side. This side has a height of S12, and hypotenuse is the length of S1, which is norm of S1. So cosine B will be S12. Let me write the 2 properly. S12 divided by the norm of S1. Okay, that's cosine B. And similarly, we can write sine B from the same triangle as, let me write here, sine B as adjacent by hypotenuse. So the adjacent side is this side, which is S11, divided by the hypotenuse, which is the length of S1. So that will be S11 divided by the norm of S1. Okay, so we have written cosine A and sine A and cosine B and sine B from these two triangles. Okay, from triangle ABC, we have found the cosine of the angle A and the sine of angle A. Similarly, from triangle ADE, from this triangle, we have determined the cosine and sine of this angle B. Okay, now we know that our theta is A minus B, so we need to find cosine A minus B, and that will give us cosine theta. So that's what we are interested in doing. So since theta is equal to A minus B, so we can now write cosine theta as cosine A minus B, and we can use the trigonometric identity of cosine A minus B as cosine A cosine B plus sine A sine B. Now we have the values for cosine A, cosine B, sine A, sine B from here. Cosine A, cosine B, sine A, sine B in terms of the vector elements and the lengths of the vectors. So we can substitute them, and we will get cosine theta as, so cosine A is S22 by norm of S2, so that's S22 divided by the norm of S2 multiplied with cosine B. So what is cosine B? Cosine B here is S12 by the norm of S1, so into S12 divided by the norm of S1 plus sine A sine B. Sine A is S21 by the norm of S2, so that's S21 by the norm of S2 into sine B, and what is sine B here is S11 by the norm of S1, so into S11 by the norm of S1. Okay, so we have this as our cosine theta, so we just need to simplify this. We'll get it as, if you notice here, the norm of S1 into norm of S2, right, is a common factor in both these fractions here, so we can have this as our LCM. So we'll we can have that as our LCM here as norm of S1 into norm of S2. Okay, I'll put a dot here to indicate that there is a product here. So norm of S1 into norm of S2 becomes our LCM. So we'll have S12 into S22, S12 into S22 plus S11 into S21. Okay, that's basically so. What do we have in the numerator here is nothing but the multiplication of the vector for S1 with the vector for S2, right? So S12 into S22 plus S11 into S21, we can rearrange these terms as S11 S21 plus S12 S22 divided by the norm of S1 into the norm of S2. So S11 S21 plus S12 S22 is nothing but the dot product between the vectors, the signal vectors S1 and S2, right? So if I have I'm just going to write it here very quickly. S1 as S11 S12, and if I have S2 as S21 S22, so S11 into S21 plus S12 into S22 is nothing but S1 transpose into S2 divided by the norm of S1 into the norm of S2, right? So this term what we have here in the numerator is nothing but the dot product between S1 and S2, and that is equal to the that divided by the norms of the individual vectors gives us the cosine of the angle theta between them. Okay, so S1 transpose into S2 divided by norm of S1 into norm of S2 is our cosine theta. So therefore we can write that the angle theta between any two signal vectors, if we can call the theta between those two signal S between S1 and S2, we have this. If instead of S1 and S2, between any Si and Sj, between any Si and Sk, we'll write this theta as theta Ik, right? So the cosine of theta Ik is Si transpose into Sk divided by the norm of Si into the norm of Sk. So we can write that in a general form as in general, the angle theta Ik between signal vectors Si and Sk is cosine theta Ik is given as the dot product of the two signal vectors, which is Si transpose into Sk divided by the product of their norms. So the norm of Si into the norm of Sk. Okay, so we have this general expression for the cosine of the angle between the two vectors. So this numerator term what we have here is nothing but the dot product of the two vectors. So if you write this, okay, this is in terms of the vectors, that is the same as the dot product in terms of the time domain signals, right? So we can write this numerator term Si transpose into Sk as integral 0 to t Si of t into Sk of t dt, right? That is basically the dot product based on their time domain representation. That is when the signal is represented as a function of time. We have this vector representation when we have the signal as in a vector form like we have shown here, okay, like this vectors, okay. And if we have it as a function of time, then we can compute this dot product in this way. And the denominators have the norms. The norm is nothing but the square root of energy, right? So in terms of the signals, Si, the norm of Si is nothing but the square root of the energy of Si of t. So the energy in terms of the function of time for Si, it's Si of t square integrated from 0 to t dt, and because it's the norm is the square root of the energy. So what we have written here on the right side is the energy, so we need to take the square root of this. So that's our energy under the root, that is our norm of Si. Similarly, the norm of Sk is integral 0 to t Sk square of t dt, okay, under the root. So again, we have depicted that in terms of the actual signals themselves, okay. We've seen it in terms of their vector representations. Now I'm trying to bring it back to our signal representations, and we'll substitute for these, okay. So cosine theta Ik, if we substitute this in place of the vectors, and the norms can be replaced by their square roots of the energies in terms of their time domain representations, and we'll get the angle between the two, right? And we are going to simplify this and get some more intuition into these equations, into the angle between the two signals, okay. Basically what we are going to do now is we are going to rewrite this equation cosine theta in terms of these time domain functions now. So we can write that as cosine of theta Ik can be written as, the numerator is the dot product, so it's integral 0 to t si of t into sk of t dt divided by the product of their norms. So the product of the norm of the first signal is the norm of the first signal is integral 0 to t si square of t dt. That's the energy, so the norm is the square root of energy into the norm of the second signal, which will be integral 0 to t sk square of t dt under the root, right? Because without the root, it represents the energy. We want the norm. So basically, we have written this cosine of the angle between the two vectors in terms of the actual time domain functions of time, in terms of the signals represented as functions of time. So now we are going to simply take these the denominator terms here to the left with the cosine theta, and we get an equation for the dot product as we'll get it as integral 0 to t si of t into sk of t dt as these terms, integral 0 to t si square of t dt, and that's under the root with integral 0 to t sk square of t dt under the root into cosine theta, right? Into cosine theta ik. So we have just rearranged this equation, and we've got this dot product in terms of their norms. So the dot product between two signals is nothing but the norm of the first signal into the norm of the second signal into the cosine of the angle between those two signals. Now this cosine theta term here can take a maximum magnitude of 1, because when theta is 0, it will be 1, and when theta is 180, it will be -1. So the magnitude of cosine cannot exceed 1, right? So it is always going to be the magnitude of cosine theta will not exceed 1, and therefore that means this term on the right hand side is getting multiplied with some value which is less than 1. Okay, so when it is getting multiplied with less than 1, basically what we will notice is that for example, if this is some value, is equal to, if we call this is these two terms, the product of these two terms has some value a times cosine theta, and this is going to be less than 1, a times 0.9 or a times 0.8. So this is going to be the product of these two multiplied with some number less than 1. So that means this term is less than this term, the product of these two, right? So this dot product is going to be less than the product of the two norms of these signals. That is what we deduce from this relationship, because cosine theta will never exceed 1. It will be equal to 1 only when theta is equal to 0. Okay, so what we deduce from here is that since the magnitude of cosine theta ik is going to be less than or equal to 1, that means this term is less than or equal to the product of these two norms. So we say that integral 0 to t si of t into sk, let me write that properly, into sk of t dt is going to be less than or equal to the product of these norms, right? So integral 0 to t si square of t dt under the root. So for the root, just to keep the notation a bit cleaner, I'm going to put power half. So that's root into integral 0 to t sk square of t dt under the root, right? So root means power half. So we have this relationship because we know that cosine theta magnitude cannot exceed 1. So we will have this relationship that the dot product of the two signals is going to be less than or equal to the product of their norms. Okay, this is nothing, the square root is nothing but the norm of Si, and this is the norm of Sk. So the product of the norms is going to be greater than the dot product. That's what this equation means. And this inequality that we have here, okay, this is an important relationship in signal processing and in communication that we come across, and it is called as the Schwarz inequality. Okay, so this relationship that we have here is called as the Schwarz inequality. Let me write that: SCHWARZ, Schwarz inequality. Okay, so the equation that we have here, this equation denotes the represents the Schwarz inequality. So I'll just put a nice box around it so that it is highlighted very clearly. So this equation that we have here, okay, that's called as the Schwarz inequality equation. Okay, now when will the left hand side be equal to the right hand side? Okay, when will these two be equal? These two will be equal to each other when theta is 0. So when theta is 0, cosine theta will be 1, and when cosine theta is 1, this LHS is equal to RHS. That means this is equal to this. This equality will apply only when theta is equal to 1. For all other values of theta, this dot product is going to be less than the product of their norms. Okay, so let's write that down. See, equality applies in the Schwarz inequality equation only when theta equals 0, or when theta equals 180. When theta equals 180, that means the vectors are going to be in opposite directions, right? So let's take the case when theta equals 0. That means when theta equals to 0, from the diagram, okay, where is our diagram? Okay, from the diagram, when theta equals 0, that theta is 0 means both the vectors are on the same line. Okay, there is no angle between them. They are not two different lines here. So when theta is 0, both the signal vectors will be on the same line. Okay, and that is what we are going to show here. So when theta equals 0, that means the signals or the vectors representing those signals are in the same direction. That means they are on the same line. They may have different lengths, but they are in the same direction. So if I denote one of them as here, okay, up to here it's S1, and then let's say up to here is our S2. So they are having different lengths, but they are in the same direction. That's why the angle between them is 0. So in that case, we'll have the left hand side to be equal to the right hand side in the Schwarz inequality. So this equal to condition will apply only when this theta equals 0. And what that means is that the signals S1 and S2 are proportional to each other. They are in the same direction and proportional to each other. For example, roughly, let's say S2 is 3 times S1. Okay, so if this is the length of S1, that's 2 times S1, that's 3 times S1, right? So when theta is 0, it means that the signals are proportional to each other. In this case, we can say S2 is 3 times S1, or S1 is 1 by 3 times S2, right? So there is some proportion between the two signals. So it means that that is the signals S1 of t and S2 of t are proportional to each other. Okay, or we can write that as, for example, in this case we can write S2 of t is equal to some constant times S1 of t. Okay, or vice versa. Okay, or we can say S1 of t is some constant times S2 of t. Okay, now from our example, we can say that S2 of t is 3 times S1 of t approximately, by looking at our diagram, right? So S2 is 3 times longer than S1 approximately, right? So the C here takes on 3, or we can say S1 is 1 by 3 times S2 of t. So this C here takes 1 by 3, right? So in other words, we say that the signals are proportional to each other. That's when the angle between them will be 0. And in that case, the equality will apply in the Schwarz inequality equation. And like that, we may have multiple signals which have angle 0 between them. So maybe that's S1, that's S2, and we can have another point here which will make that length as S3, and so on. So we can have multiple signals which may have angle 0 between them. But when the angle between them is 0, it would automatically mean that the signals are proportional to each other. Okay, so we have seen the geometric representation of the signals, and we have seen how to compute the energy of a signal from its geometric representation, and how to compute the length of the signal, how to compute the dot product of the signal between two signals from the geometric representations. And we've also seen how to compute the angle between two signals based on their geometric representation. So the angle between two signals based on their vector representation is nothing but the dot product of the two vectors divided by the product of the norms of the two vectors. Okay, that is the length of the two vectors, right? Next, what we are going to do is we are going to focus now on a procedure to find these axes. If you recall from the previous lecture, we said that in the geometric representation we choose these axes which are denoted as the basis functions, phi1 of t, phi2 of t, phi3 of t, and so on. These are our basis functions. And the basis functions have certain properties. First is that they are orthogonal to each other. That means the angle between them is 90 degrees, or the dot product of them between them is 0. And they have unit energy. Each of the basis functions has unit energy. So that is why we call them as orthonormal basis functions. Now we will now focus our attention to a procedure to find out basis functions for signals which would satisfy these properties of being orthogonal and unit energy. That is, how to find orthonormal basis functions for a given set of signals. So if we are given a set of signals, S1 of t, S2 of t, S3 of t, and so on, for that set of signals, how do we find a set of basis functions which are orthonormal? And that is what we are going to do next. And the procedure to find that is called as the Gram-Schmidt orthogonalization procedure. And today I will give you an introduction to that procedure, and in the next lecture and video I will focus on taking an example of signals and computing using this procedure to compute the basis functions and verify that those basis functions that we develop have the properties of being orthogonal and unit energy. So we will now begin with our procedure to find the basis functions, phi1 of t, phi2 of t, and so on up to phi n of t. And the procedure is called as the Gram-Schmidt orthogonalization procedure. So basically it's a process, okay, it's a procedure to find the basis functions that is the axis that we are going to use for our geometric representation of our signals. Okay, so we want to basically find phi j of t for j going from 1 to n. So we want to find the n basis functions, and we are going to do so for our m signals. So we have a set of m signals, and those m signals will be represented by a set of n basis functions, or using a set of n basis functions, and the number of basis functions is always going to be less than or equal to the number of the signals that we have itself. Okay, so the properties that these basis functions must satisfy is that they should be orthonormal. So orthonormal basis functions. Now, what do we mean by orthonormal basis functions? That means the dot product of any two basis functions, okay, that is integral 0 to t phi I of t into phi j of t, okay, that's j, dt is equal to 0 if I is not equal to j, and it's equal to 1 if I equals j. Okay, so that's the properties that the basis functions must satisfy in order to be called orthonormal basis functions. Okay, their dot product should be 0 and their energy should be 1. When I equal to j, we get integral phi I square of t dt. That gives us the energy, and so the energy is 1. That's called unit energy. So we want to compute the basis functions, the n basis functions for a given set of m signals that we have. Okay, so that's what we are trying to do. So what we are trying to do here is to find the n basis functions given a set of m signals, and the basis functions that we find should satisfy this property of being orthonormal. That is, the dot product between any two basis functions should be 0. That is, they should that means the angle between them should be 90 degrees, right? So when the angle between two signals is 90 degrees, if you recall, the angle which is cosine theta, when it's 90 degrees, then the dot product will become 0, because when theta is 90 degrees, cosine 90 is 0, 0 into anything is 0, so the dot product becomes 0, right? So that's what we mean. That dot product should be 0. That means the angle between the basis functions is 90 degrees, and the energy of each of the basis functions should be 1. Okay, so we are going to give the steps that we should follow, and those steps are given by this by these mathematicians Gram and Schmidt, and it's called as a Gram-Schmidt orthogonalization procedure to find the basis functions phi 1, phi 2 up to phi n of t that satisfy these properties to be orthonormal basis functions. So what we do in this procedure, that is the Gram-Schmidt orthogonalization procedure, is we first define what we call as some intermediate functions gi of t. So we have a definition for some intermediate functions, and the intermediate function gi of t is given as gi of t as equal to the signal si of t minus the summation of sij into phi j of t for j equals 1 to I minus 1. Okay, we don't go up to n, but up to I minus 1. Okay, so for the first signal s1 of t, we'll get the corresponding g1 of t as simply s1 of t, because this summation term will be 0, because j equal to 1 to I minus 1. So I is 1. When I is 1, it's 1 minus 1 is 0. So 1 to 0. You can't go backwards here, right? So this term will become 0. So g1 of t will basically be s1 of t. And then we can similarly find g2 of t as s2 of t minus j equals 1 to 1, because 2 minus 1 will become 1. So si1 into phi 1 of t. So it's only one term here in the summation. When I equals 3, then you'll have two terms and so on. So we have to use this equation to find what is called as the intermediate function gi of t. That's the first step. And the second step is, once we have found the intermediate function gi of t, then we will find the corresponding basis function phi I of t. So from gi of t, we obtain the basis function phi I of t. Phi I of t as phi I of t is equal to gi of t, the intermediate function, divided by the norm of the intermediate function. And the norm of the intermediate function is nothing but the square root of its energy, right? Let me write this: norm of the intermediate function, right? Norm of gi of t. So that's nothing but gi of t divided by integral 0 to t gi square of t dt under the root. Okay, that's the square root of energy. The square root of energy is the norm of the signal. So integral gi square is the energy, the square root of energy is the norm. So we get the first basis function corresponding to the first intermediate function. So we compute g1 of t, and then from g1 of t we will find phi 1 of t. Then we will find g2 of t, and from g2 of t we can get phi 2 of t, and so on. Okay, so that's the procedure to find the basis functions, and then we'll verify that those basis functions that we obtain indeed satisfy the properties of being indeed satisfy the properties of being orthonormal. So let's see what happens when we put different values of I here. Okay, when I equal to 1, when I equal to 2, and so on, what do we get for each of the intermediate functions? And then from there we can find out the basis function. So that's our equation for the intermediate function. And when I equals to 1, that is for I equals 1, we get g1 of t as s1 of t minus summation j equal to 1 to I minus 1. I is 1, which is 1 minus 1, s1j into phi j of t. Now 1 minus 1 is 0 here, right? So we can't go from 1 to 0 in the summation, right? The index can't go from 1 to 0. So that means this whole term is equal to 0 basically. So we get for I equal to 1, g1 of t is equal to s1 of t, which is the first basis function. The first intermediate function is the same as the first signal that we have, and from that we can write the first basis function as phi 1 of t, which is g1 of t divided by the norm of g1 of t, right? So that's g1 of t divided by the norm of g1 of t. And since the intermediate function g1 is equal to the first signal s1 of t, so that's simply equal to s1 of t divided by the norm of s1 of t. So the first basis function is nothing but the first signal divided by the square root of the signal's energy, because the norm of the signal is nothing but the square root of its energy, right? So let me just write that since the norm of g1 of t is equal to the square root of the signal's energy, right? The square root of E1, right? We can therefore write the first basis function phi 1 of t Let me elaborate that a bit further just to avoid any confusion. So the norm of G1 of t is nothing but the norm of S1 of t, which is nothing but the square root of the energy of the signal S1, which we call as square root of E1. E1 is the energy of S1 of t, and therefore the norm of S1 of t is the square root of its energy. And from that we basically have our first basis function phi1 of t to be equal to the signal S1 of t divided by its the square root of its energy, right? So that's S1 of t divided by the square root of the energy of S1 of t. Okay, so where E1 is the energy of S1 of t. So let me write that. So now that we have our first basis function defined as this, which is basically the first signal divided by the square root of its energy, we can now write the signal S1 of t in terms of the basis function. So we can say that this equation can be written as S1 of t. Let me write that properly. S1 of t is equal to square root of E1 times phi1 of t. Now if you recall that we can write our signal in terms of the vector elements and the basis functions, right? S1 of t is S11 phi1 plus phi1 of t plus S12 phi2 of t plus S13 phi3 of t, and so on. Here we clearly have S1 of t as simply something into phi1 of t, but there is no it has no projection on phi2 of t. That means the projection on phi2 of t is basically 0. So this E1, the square root of E1 that we have here, is basically the first element of its vector representation. So that is basically, we can call it as S11 phi1 of t. So if we have this signal S1 of t in vector form as S11, S12, S13 and so on, this S11 is basically square root of E1, and because S1 of t does not have any other projections on phi2 and so on, this S12, S13 are all going to be zeros. Okay, that's what it means. So the square root of E1 is basically the first element of the vector representation of the signal S1 of t. So that's S11. So S11 is nothing but the square root of E1. So therefore we say that, in other words, that is S11 is equal to the square root of E1. So from this we have now got the representation of the first signal in terms of its vector, and we also found the the basis function phi1 of t for this set of signals, the first basis function. Okay, and we want to verify now that this first basis function that we have found is having unit energy, because all the basis functions should satisfy the property of being orthonormal. That means the energy of the basis function should be 1, and the dot product with another basis function should be 0. So we'll first verify that our phi1 of t has unit energy, and once we find phi2 of t, we can check whether the angle between those two is 90 degrees or the dot product is 0, right? So let's verify the energy of phi1 of t. So let's do that computation. Energy of phi1 of t is integral 0 to t phi1 square of t dt, and phi1 is given as S1 of t divided by square root of the energy of S1 of t, which is square root of E1, right? So we'll just square that. So 1 by square root of E1 is 1 by E1 integral S1 square of t dt from 0 to t, right? So we just substituted in place of phi1, we have put s1 of t divided by square root of e1. So when we square that, this is square, the square root disappears, and square of s1 of t is s1 square of t. So within the integral we have this function of time. So that's nothing but the energy of s1 of t, which is nothing but e1. So that is basically 1 by e1 into e1 to E1, which is equal to 1. So we clearly see that the energy of the first basis function is E1 by E1, which is equal to 1. So it satisfies the property of having unit energy. So phi 1 of t has unit energy. Okay, now we need to next find the second basis function. So we will again take the expression for the intermediate function gi of t, and we'll put I equal to 2 in that, and that will give us the second basis function phi 2 of t. Okay, so let's find let's write the equation for gi of t once again. So we are going to find the second basis function now. So we need to first compute the intermediate function g2 of t, and for that we'll use the general expression for gi of t, which is equal to si of t minus summation sij into phi j of t for j equals 1 to I minus 1. Okay, now we want to find g2 of t and then phi 2 of t. So we want to put I equals 2 here. So we'll put for I equals 2, we'll get g2 of t here. So g2 of t as s2 of t minus summation in place of I we have to put 2, so that's s2j into phi j of t, and that goes for j equal to 1 to I minus 1. I is 2, 2 minus 1 is 1, so it's j equals 1 to 1. So that means it takes on only for j equal to 1. There's only one value of g here, which is from 1 to 1. Okay, so that is basically s2 of t minus s21 phi 1 of t. So that becomes our second intermediate function g2 of t, which is s2 of t minus s21 phi 1 of t. And from this g2 of t we can now compute the second basis. So what we have here is we just substitute I equals to 2 in our equation. That gives us g2 of t as s2 of t minus summation j equal to 1 to I minus 1. I is 2, so 2 minus 1 is 1. So from 1 to 1, sij, in place of I we put 2 because I is 2, s2j into phi j of t. Now j goes from 1 to 1, right? So that means j takes on only one value, which is 1. So that becomes there's no summation here because it's only a single term now, because j takes on only one value, which is 1. So s21 into phi 1 of t. So we have that single term here, and from that g2 of t we can now compute the basis function phi 2 of t as g2 of t divided by the norm of g2 of t. So we need to first compute the norm of g2 of t and then substitute it here to get our second basis function phi 2 of t. So to compute the norm of g2 of t, we'll do it in this way. So we'll first find the square of the norm, that is the energy of g2 of t, and then at the last step we'll take the square root to get its norm, right? So we'll see, that makes it easier. So that's g2's the square of the norm, that's g2 of t norm squared, is nothing but the energy of g2 of t. So integral 0 to t g2 square of t dt, and g2 of t we have it here, so we're just going to substitute that. So we'll get integral 0 to t g2 square, that will be s2 of t minus s21 phi 1 of t, the whole square dt, right? So we just need to square this term and evaluate this g2 of t norm squared. So that will give us, so this is basically of the form a minus b the whole square, right? That's a minus b the whole square is a square plus b square minus 2ab. So that is exactly what we will apply now. So that will become equal to integral 0 to t s2 square of t, that's a square, plus b square. B square will become integral s2 1 square into phi, let me write that clearly, s2 1 square into phi 1 square of t dt from 0 to t minus 2ab. That's so that's minus 2 into ab integral s2 of t into s21 phi 1 of t dt integral from 0 to t, right? So that's a square plus b square minus 2 times ab minus 2ab. And now we can see what these evaluate to. So integral s2 square of t is nothing but the energy of s2 of t, so which we can call as E2. So that is basically E2. Now the second term here is simply s2 1 square, because okay, let me write that, plus s2 1 square, we can take it outside the integral because it's just some number. So s2 1 square integral phi 1 square of t dt from 0 to t. And we have seen there earlier when we did phi 1 of t that the energy of phi 1 is equal to 1. Okay, so we verified that in our previous slide. The energy integral phi 1 square of t dt is 1. So this term is going to be equal to 1. And then we have minus 2 times s2 of t into phi 1 of t. Okay, s21 is a number, so minus 2 times s21 integral s2 of t into phi 1 of t dt. So from 0 to t. So basically what this is the projection of s2 onto phi 1. So that is nothing but s21. Okay, s21 is nothing but integral 0 to t s2 of t into phi 1 of t. So refer to the previous slides from the previous lecture where this equation is specified. Okay, so this is nothing but s21. So effectively what this equation becomes is E2 plus s21 square, and this integral is 1 because phi 1's the energy of the first basis function is 1. Then we have minus 2 times s21 into this integral itself is equal to s21. Okay, because it's the projection of s2 onto the basis function phi 1. So this integral, let me mark it here, this is equal to s21. So it's minus 2 times s21 into s21. So that becomes E2 plus s21 square minus 2 times s21 square, which is equal to let me use the same line, which is equal to E2 minus s21 square. Okay, s21 square minus 2 s21 square is minus s21 square. So the square of the norm of g2 of t is nothing but E2 minus s21 square. But we are interested in the norm itself, not the square of the norm. Okay, so we have the square here, so we need to get rid of the square, so we need to put a square root here, right? So the norm therefore becomes the norm of g2 of t is therefore the square root of E2 minus s21 square. Okay, so that should be in the square root now. So that's the norm of g2 of t. So now using this expression for the norm of g2 of t, we can now find our phi 2 of t, which is g2 of t by its divided by its norm, and g2 of t is this. So we'll write this divided by the norm of g2 of t. So therefore we can write our basis function phi 2 of t, which is g2 of t divided by the norm of g2 of t, which is therefore equal to s2 of t minus s21 phi 1 of t divided by e2 minus s21 square under the root, right? So that's our second basis function phi 2 of t, which is equal to g2 of t divided by the norm of g2 of t. This is what we get. Okay, s2 of t minus s21 phi 1 of t divided by the square root of e2 minus s21 squared. So we have the second basis function. Now we need to check whether this basis function also has unit energy, and then we will check whether the second basis function is orthogonal to the first basis function that we had previously, that is phi 1 of t. That is, the dot product between phi 1 and phi 2 should be equal to 0. Okay, we need to verify that, and that's when it qualifies as being a valid basis function. So let's see if that can be proved. So let us first find the energy of this basis function phi 2 of t. So energy of phi 2 of t is integral 0 to t phi 2 square of t dt, right, which is nothing but phi 2 square is nothing but g2 by the norm of g2, right? So it's integral g2 square of t dt divided by the norm of g2 square. That is the norm squared of g2 of t, because if you recall here, we have the definition for phi 2 as g2 of t divided by the norm of g2 of t. So phi 2 square of t will be g2 square by the square of the norm. That is exactly what we have written here in place of phi 2 of t. So that integral goes from 0 to t, and basically we are saying that the denominator can be taken outside the integral because it's just a number. So norm squared is energy, right? Energy of g2 of t, so that's g2 of t norm squared, okay, into integral 0 to t g2 square of t dt. Now integral 0 to t g2 square of t dt is nothing but the energy of g2 of t, and the denominator here is also the energy of g2 of t, and we've seen earlier that the energy is the square of the norm. So this is basically the same as what's in the denominator, right? So this integral here is basically the same as what's in the denominator. So basically we get norm of g2 of t squared divided by the norm of g2 of t square, which is equal to 1, because this term here is nothing but the norm square of g2 of t. So that's equal to g2 of t norm squared, right? So that's the energy of g2 of t basically. So we see that it's the same as what's in the denominator, so this whole thing becomes equal to 1. So we have verified that the energy of phi 2 of t is indeed equal to 1. The next thing we need to verify is that the dot product between phi 1 of t and phi 2 of t is 0. So we have earlier got our first basis function phi 1 of t given as s1 of t divided by the square root of e1, and we need to verify now whether phi 1 of t and phi 2 of t are orthogonal to each other. That is, the dot product between them should be 0. So we need to show that phi 2 of t is orthogonal to phi 1 of t. In other words, we need to show that the dot product, okay, between phi 1 of t and phi 2 of t is equal to 0. So that's integral 0 to t phi 1 of t into phi 2 of t is equal to 0. But what we will do now is we will make some simplifying process for this. So we notice that phi 2 of t is equal to g2 of t. This is what we defined earlier, divided by the norm of g2 of t, right? So that means what we notice here is that phi 2 of t is proportional to g2 of t, because this denominator is nothing but a number. So like we saw earlier for the angle between two vectors, when the angle is 0, we said that they are proportional to each other, right? It is each is the other multiplied by some factor, right? That factor there is the denominator norm term, right? That means the angle between them is 0. That means they are both in the same direction. So we are going to exploit that fact here. So we see that the basis function phi 2 of t is proportional to the intermediate function g2 of t, because it is some c times g2 of t, and that c is 1 by the norm of g2 of t, right? So we see that phi 2 of t and g2 of t are in the same direction. So rather than finding the angle between phi 1 and phi 2, we will find the angle between phi 1 and g2 of t, and if we can show that g2 of t and phi 1 of t are orthogonal, then automatically phi 2 of t and phi 1 of t will also be orthogonal to each other, because phi 2 and g2 are in the same direction. Okay, so we say that since phi 2 of t is proportional to phi 1 of t, phi 2 of t and g2 of t are in the same direction, right? It means phi 2 of t and g2 of t are in the same direction. So because they are in the same direction, the angle between phi 2 of t and phi 1 of t will be the same as the angle between g2 of t and phi 1 of t. So therefore, the angle between phi 2 of t and phi 1 of t is the same as the angle, let me write that, as the angle between g2 of t and phi 1 of t. Okay, so now if we can prove that g2 of t and phi 1 of t are orthogonal, that is, their dot product is 0, then it automatically will mean that phi 2 of t and phi 1 of t are also orthogonal. So that is exactly what we are going to do now. So we are going to find the dot product between g2 of t and phi 1 of t. So that dot product is given as integral 0 to t g2 of t into phi 1 of t dt. Okay, so that's basically going to simplify our task, okay, of proving orthogonality. And since we know g2 of t, okay, we have our definition for g2 of t over here. Where is that? Okay, we have g2 of t as s2 minus s21 phi 1 of t. So we're just going to substitute that here in place of g2 of t. So that is going to be equal to integral 0 to t. G2 of t is S2 of t minus S21 times phi 1 of t. Okay, that's G2 of t into phi 1 of t dt, right? So that's our integral to compute the dot product between G2 and phi 1. And therefore, we can simplify that as integral 0 to t S2 of t into phi 1 of t, S2 of t into phi 1 of t. So we're just multiplying this term with the term outside here, S2 of t phi 1 of t, and we'll split the integrals dt minus S21 can be taken outside. So we're going to multiply the second term with this term outside. So that will give us S21 integral phi 1 of t into phi 1 of t, which is phi 1 square of t dt for integral 0 to t. Now integral phi 1 square is nothing but the energy of the basis function phi 1, and which is equal to 1, which we have already shown. So that integral is equal to 1. So that becomes S21 times 1. And what we have on the left hand side here, integral 0 to t S2 of t into phi 1 of t, is nothing but the projection of S2 of t onto the basis function phi 1 of t. So that is basically equal to S21. This integral, this whole thing is equal to S21 minus S21, and this integral is equal to 1. Okay, that's equal to 1. So S21 minus S21 is equal to 0. That means the dot product between G2 of t and phi 1 of t is 0. So therefore G2 of t is orthogonal to phi 1 of t. That means the angle between G2 and phi 1 is 90 degrees. And since G2 and phi 2 are in the same direction, the angle between phi 2 and phi 1 is also equal to 90 degrees, because in that case that dot product is also 0. Okay, proving it this way makes it a lot easier in our calculations. Okay, so since we say that since G2 of t is orthogonal to phi 1 of t, it implies that phi 2 of t is also orthogonal to phi 1 of t. Okay, so the reason for that is because since phi 2 of t is proportional to G2 of t, it is some constant times G2 of t, where this constant c is nothing but 1 by the norm of G2 of t. Okay, so phi 2 of t is G2 of t divided by the norm of G2 of t, right? So that 1 by the norm of G2 of t is this constant, right? So it's basically phi 2 of t is proportional to G2 of t. That means phi 2 and G2 are in the same direction. So if phi 2 and G2 are in the same direction, it means that whatever is the angle between G2 and phi 1, that is the same angle exists between phi 2 and phi 1 of t. Okay, so hence we have proven that phi 2 of t is orthogonal to phi 1 of t. So the two basis functions are orthogonal to each other. So likewise we can compute the third basis function phi 3 of t and phi 4 of t and so on. But we, rather than going through the process of these calculations, we can just expand or deduce from our previous calculations how this pattern is going to emerge. Okay, there is an emerging pattern coming up in these things. So let's see what that pattern is, and based on that pattern we will see what is phi 3 of t and hence phi 4 and so on. So let's write down the equations for the basis functions we have found so far. So for the first basis function phi 1 of t, we got it as S1 of t divided by the energy E1, the square root of the energy of S1 of t. Then we found the the basis function phi2 of t as s2 of t minus s21 phi1 of t. Okay, that's phi2 of t is s2 of t minus s21 phi1 of t divided by the square root of e2 minus s21 square. Okay, so we see that in phi1 of t, in the numerator we had only s1 of t, so the denominator had just the energy of that s1 of t. In the second basis function we have s2 of t minus the minus s21 into phi1 of t, right? Correspondingly, the denominator corresponding to s2 of t we have e2, and corresponding to this term we have s21 square, right? Similarly, for phi3 of t we'll have additional terms, and correspondingly we'll have additional terms in the denominator as well. So we are going to get our phi3 of t as s3 of t minus, rather than having just a single term in the summation when computing the gi of t, we are going to have two terms now. So it will be a summation of those two terms, which will be s31 phi1 of t plus s32 phi2 of t. So that's going to be the term. So if we remove this bracket, it will become s3 of t minus s31 phi1 of t minus s32 phi2 of t, and accordingly, just as we had the denominator terms here, we'll need to insert the corresponding denominator terms here. So corresponding to s3, we'll have the square root of e3, so the square root will be there, so in place of e2 we'll have e3, and here we have s31, so we'll have minus s31 square, and here we have s32, so that will be minus s32 square, right? So we're just going to it's going to emerge as the same pattern. You can calculate and verify the same. Okay, I've done the example for computing two basis functions, and the same ideas apply for the third, fourth, and fifth, and so on. So it will become e3 minus s31 square minus s32 square under the root. Okay, so that will be our third basis function, and likewise we can keep going on up to n basis functions, and n is going to be less than or equal to m. So the number of basis functions n is going to be less than or equal to m. Now, when will the number of basis functions be equal to the number of signals that we have in our set? That will be the case. N will be equal to m when the signals are linearly independent of each other. So when the signals s1 of t, s2 of t, s3 of t up to sm of t are independent, linearly independent, then we will have the number of basis functions n to be equal to the number of signals m. When they are not linearly independent, then we will have n to be less than m. Okay, so let's make that statement here, or let me use another page for that. So as we said, n will be equal to m when the signals are linearly independent. Okay, so let me highlight that. So when we have the signals s1, s2, s3, s4 up to sm of t, when the m signals are linearly independent of each other, then the number of basis functions will be equal to the number of signals we have. When they are not linearly independent, then when the signals are not linearly independent, then n is going to be less than m. So basically what will happen is the intermediate functions that we compute gi of t, they will become equal to 0 for I greater than n. Okay, so therefore we will not have the corresponding basis functions for I greater than n. That is what will happen. Okay, so that's the Gram-Schmidt orthogonalization procedure, where we can compute the basis functions by first finding an intermediate function gi of t, and then the basis function can be computed as the intermediate function divided by its norm. And like that, we for different values of I, we can compute the different basis functions phi1, phi2, phi3, and so on. And that's the standard procedure. And once if we follow this procedure, we will end up with the basis functions which are orthonormal basis functions. That is, the basis functions will be orthogonal with respect to each other. That is, their dot product will be 0. The dot product between any two basis functions will be 0, and each of the basis functions will have an energy value which is equal to 1. So that's what we call as orthonormal basis functions. And this procedure that we described today is called as the Gram-Schmidt orthogonalization procedure, which is used to find orthonormal basis functions. Okay, in the next lecture I'll be taking some signals, a set of signals, s1 of t, s2 of t, up to say sm of t, some 4 or 5 signals, and then we will compute the orthonormal basis functions. So we will basically follow this procedure to find the basis functions for a set of signals and verify all the properties of those basis functions as well. And we'll see how we can represent those signals in terms of the basis functions as vector forms. Okay, we'll do that in the next lecture.